rearrangement reaction. Now, rearrangement reaction is an organic reaction that involves the migration of one group or migration of a group or an atom from a center, which is a migration origin, to another, which is a migration terminus. I'll say it involves the migration of a group or an atom from a center, which is the migration origin, to migration terminus. Okay, so it's an organic reaction where a migrating group or a group is migrated from one point to the other. The point where it's starting from is the origin. The point where it's going to end is the terminus. Right? Now we have types of rearrangement reaction. Types of rearrangement reaction. We have two major types of rearrangement reaction. Okay, we have the first one, what we call the intermolecular rearrangement, and we have the second one, the intramolecular rearrangement. Now basically, what is the word inter, or what does it mean for something to be intermolecular? It's a case where the migrating group, right, is actually detached from its origin, right, and then moved to its terminus. So it's a type of rearrangement where the migrating group is detached from its origin and placed in another position, right? Okay, now what is intramolecular? Intramolecular is a case where the migrating group is never detached from the compound. Now let's look at classifications of rearrangement reaction. Right, we have different classes of rearrangement reaction. Now this is dependent on where it is coming from and where it is going to. So we have classification of rearrangement with respect to migration origin and the terminus. All right, so the first one we have rearrangement to electron deficient carbon center. All right, so this basically, carbon deficient is basically carbon that has a positive charge, because when an atom is deficient of electrons, you're going to see a positive charge. Now the second one is rearrangement to in this case now, carbon is seen to have a negative charge. So these are the various classifications of rearrangement reaction with respect to the migration origin to migration terminus. All right. So we're going to take them one after the other. We're going to start with the first one. Please remember, just in case of exam, they might ask you the type of rearrangement in which the migrating group is never detached from the compound is dash. The answer is intermolecular, right? So the answer is intramolecular. Intramolecular, the migrating group is never detached from the compound, but in intermolecular, a migrating group is detached from one point to the other. So we're going to be looking at the first one, rearrangement to electron deficient carbon, all right? Rearrangement to electron deficient carbon atom, all right? So now, what are the various types of, under this guy we have several types of rearrangement reaction, all right? Now this is basically a case where the terminal or the terminus where the migration, where the rearrangement is going to end, will have a carbon that has a positive charge, okay? So the first one we have, number one, we have Wagner-Melwin rearrangement. The second one we have the Pinacol. The third one we have the azomethane rearrangement. And the fourth one we have benzylic acid rearrangement. All right. So these are the four rearrangements that are placed under electron deficient carbon atom. Now let's look at the first one. Let's look at the first one. Wagner-Melwin. Now, this is particularly a type of rearrangement reaction that is used to, rearrange carbocations. It involves, this particular Wagner-Melwin involves the rearrangement of a less stable carbocation to a more stable carbocation. Right? So I said Wagner-Melwin is a type of rearrangement reaction that is used to rearrange a less stable carbocation to a more stable carbocation. Now, do not forget that carbocation, we have the primary carbocation, we have the secondary, and we have the tertiary. Tertiary is the most stable amongst the three of them. So tertiary is more stable than secondary, secondary is more stable than primary. So imagine a case whereby I'm carrying out a reaction that consists of series of steps, right, where an intermediate will be formed before you get to your final product. If the intermediate that is forming happens to be a carbocation, in organic chemistry we have series of intermediates, we have radicals, radicals could be an intermediate, we have anions, and we have carbocations. So imagine a case whereby you form an intermediate that is a carbocation, that is a carbon bearing a positive charge, okay? And then that carbocation turns out to be a primary carbocation, right? And there is a possibility of that carbocation to be rearranged to secondary or to be rearranged to tertiary. The rearrangement is going to occur immediately, even without you noticing it. So first, what is a primary carbocation? Let me give us an example on the board. A carbon where the carbon bearing the positive charge is attached to just one other carbon. Secondary carbocation is a case where the carbon bearing the positive charge is attached to two other carbons, which is this and this. We have a tertiary carbocation where the carbon bearing the positive charge is attached to three other carbon atoms. All right, so in this Wagner-Melwin, I said it's basically a type of rearrangement reaction mostly seen in carbocations, right, where a less stable carbocation would be rearranged to a more stable carbocation. Now, this is usually done via a 1-2 shift, right? 1-2 shift simply means you're moving a bond from position 1 and you're moving it to the next immediate position. It must not necessarily be carbon 1 and carbon 2, nope, right? It simply means that if you're moving it from carbon 1, it ends at carbon 2. If you're moving it from carbon 3, it ends at carbon 4. So you're just doing the movement within adjacent carbon atoms. All right. So we're going to take some few examples under this Wagner-Melwin so that you can understand what I mean. Now, note, I say Wagner-Melwin is actually accomplished using 1-2 shifts. This 1,2 shift can be 1,2 hydride shift. That is, you're shifting hydrogen with a negative charge. This guy can still be 1,2 alkyl shift, which most of the time the alkyl we always shift here is always methyl. This guy can also be 1,2 aryl shift. Now the aryl shift is basically the one that contains a benzene ring. Now amongst three of them, right, their migratory aptitude is different. Like the ability to migrate faster is different. Aryl migrate faster compared to alkyl, and alkyl migrate faster compared to hydride. Anyways, let's look at some few examples. Imagine I have something like this: CH3, C, CH3, CH3, and I have this. Now this particular carbocation, let's assume we form this carbocation from the first step of a reaction, right? Now remember I said there are reactions that go through several steps, right? So the moment a reaction goes through several steps, there's always a need for an intermediate to be formed. Because let's assume you're climbing upstairs, you have a third floor, 3-story building, right? For you to get to the last floor, you must pass through the middle floor. So that middle floor is actually what I refer to as intermediate. For you to get to the product, you must first of all get the intermediate. Now let's assume the intermediate turns out to be something like this. This is called a neopentyl carbocation. Now, this is a primary carbocation. Now, based on the illustration I gave us, a primary carbocation is basically a carbocation in which the carbon bearing the positive charge, the one with asterisk, is further attached to just one carbon, which is just this guy. So this carbon bearing this guy is attached just to this one carbon. So it's a primary carbocation. All right. Now, is there a possibility for this guy to migrate to a more stable carbocation, either a secondary or a tertiary? I'll show us. Now, I'm going to have something like this: 1, 2 methyl shifts. Why did I say methyl shifts? Now look at this. If I move this methyl, any one of these methyl on this carbon, let's label this carbon here: carbon A, carbon B, and carbon C. Carbon A is the carbon bearing the positive charge. That is why this guy is a carbocation. Carbon A is attached to just carbon B. That is why this guy is a primary carbocation. But can we rearrange this particular carbocation to a more stable carbocation? Yes. How do we achieve that? Now, if I migrate this alkyl group from this carbon B, any of this alkyl group from this carbon B to this guy, I'm saying 1, 2. Remember I just told you that 1, 2 is a case whereby you're moving something from a carbon to the next carbon immediately. So if I move this particular CH3 to this point, I'm going to do methyl shift, because what I'm shifting is methyl. It's going with the bond, right? Or I can use this one up here. This becomes this. I'm moving this methyl from this carbon B to carbon A. So this becomes CH3, C, CH3. This CH2 was here. I write it down. Now this CH3 that I just moved down, I can put it up here. Right? If I put this CH3 up, I can decide to either put it up here, or I can just put it at the side. The positive charge that was here initially will now be migrated, or will now move to this point now. So this was a primary carbocation, and this is now a tertiary carbocation. Why? Because this carbon bearing the positive charge is now attached to 1, 2, and 3. And that is basically what Wagner-Mewing is actually telling us. So if you notice, what are we migrating? Methyl. Where is the migration moving towards? What is the terminus of the migration? A carbon with a positive charge. Hence, the reason why we said rearrangement to electron deficient carbon. And I told us that electron deficient carbon is carbon with a positive charge. Alright? Okay. Now, what if I now come here? Let's say this is the first example. What if I come here and remove this place and I put it hydrogen? Class, hook up. What if I come here and I have this? What if an intermediate of a reaction, right? What if an intermediate of a reaction is this? Now, first and foremost, if you look at this is a primary carbocation because the carbon bearing the positive charge, which is the one with asterisk, is only attached to this. Only attached to this. All right. Now, is there a possibility of us to get a more stable carbocation? Is there a possibility for that? Yes, there is a possibility. Now, look up. It's either, look at what I'm going to do now. It's either I'm going to move this methyl, bring it to here. I'm going to move hydrogen, bring it to here. Now, I'm going to do both of them and then tell you the one that is going to be the most correct one or the one that will be the correct one. So here, if I say 1, 2 methyl shifts, I'm going to move this methyl here. All right, this becomes CH3, CH, CH2, CH3. I have moved the CH3 to this position. Here becomes a positive charge. Now, I have to come back here. I write this CH3, C, CH3, H. Now, the first one, I moved methyl. The second one, I'm going to move hydrogen. I'm showing us the possible movement, and then I'm going to tell you the one that is correct in case of exams. Now here, if I move this hydrogen here, this becomes 1, 2 hydride shifts. Because what I'm moving is hydrogen. If I move this guy to this point, this is what I'm going to have. I have CH3, C, CH3. Remember this CH, this guy was CH2 already. If this H should come add to this guy, we have CH3. And the positive charge comes here. The positive charge is going to come here. Now look at these two guys. Which type of carbocation it is? Primary, secondary, or tertiary? Now this is secondary. Because the carbon bearing the positive charge is attached to this and is also attached to this. Here, this is a tertiary carbocation. Because the carbon bearing this guy is attached to this, and to this. It's attached to 3 carbon. So between secondary carbocation and tertiary carbocation, which is more stable? Tertiary is more stable. So therefore, in this particular case now, where 2 rearrangement is possible, you're going to choose the one that will give you a more stable carbocation. So in exams, if you have done this ahead of this, you'll be wrong because your product is actually not going to be the most correct one. Right? If you were asked to give the most stable product, this is going to be the most stable product. Right? So I just had to do 2 of them. This is also very correct, but in the case of both of them, right? In the case of you have this and this, you're not supposed to go with this. This is what you're supposed to migrate, because if you migrate hydrogen, you're going to get a tertiary carbocation. If you migrate methyl, you're going to get a secondary carbocation. All right. So take note of that. All right. So the next rearrangement reaction we're going to be looking at is Pinacol rearrangement. All right. Now this is a type of rearrangement whereby a type of rearrangement whereby a vicinal diol is treated with tetraoxosulfate 6 acid. A type of rearrangement where a vicinal diol is treated with tetraoxosulfate 6 acid to give aldehydes, to give either aldehydes or to give a ketone. Now, first thing first, Pinacol is basically a name of a compound which we're going to be seeing much later. But Pinacol, this particular rearrangement, just like we said, is a case where a vicinal diol. First thing first, what is a diol? A compound that has two OH group. A vicinal diol is basically a compound that has two OH group on adjacent carbon. For example, if I have, let's say I have CH3, I have this CH3, I have OH, I have this, I have OH, and I have this. Now this is a vicinal diol. This is also a vicinal diol. If I have something like this, this is also a vicinal diol. Basically, a vicinal diol is a type of diol. Diol means two OH group. Di is two, all is OH. So a vicinal diol is a compound that contains two OH group, right? Where the two OH group are attached to adjacent carbons, right? Adjacent carbons. All right, so now this is basically what we're going to have. Now, if you treat this with H2SO4, the product we're going to have would be as follows. We're going to have CH3, C, O, now this is what we're going to have. This is a ketone, and this is a diol. I'm just using their generic name. Now, what happened here is that this CH3 migrated to this point, right? This is what we have here. And then one of these OH, one of them is going to go out, and then we now have O with double bond. So this example, this is a typical example of a Pinacol rearrangement, all right? A rearrangement whereby we move from a diol to a different compound. Do you understand? So what I'm going to be showing us is the steps on how this came about. And once you understand the step, you can apply it to actually solve any other Pinacol rearrangements. Afterwards, we look at the factors that is going to help us in a case where this particular substrate is mixed with different groups or different substrates. All right. Where did you go to? Downstairs. Just this last one. My battery is low, sir. My battery is low. So let me just finish this one, then I'll end. Are you going? Ayana, no problem. I want to branch market. I want to cook. No. How many percent? Oh, I just saw this battery. All right, so I want to explain the steps involved in Pinacol rearrangement, right? Now, after these particular steps, I'll further explain the factors, right, in the next video, in the next class. Now, first thing first, this is a reaction, CH3, CH3, OH, CH3, OH, CH3. Now, this reacted with H2SO4 and then gave us CH3, C double bonded to O, CH3, CH3, and CH3. Now let's look at this. Let's look at the solution. The first thing first is we are going to protonate one of the OH group. Now in this case now, right, they give us a symmetrical compound. That means these two OH group are similar because they are attached to the same CH3 and CH3. Assuming they are giving us something different, right, which I'm going to use in the next video or in the next class or in the next example. If they give us a substituent that is not the same, there are some conditions you must consider before you choose one of these guys to protonate. But so far, based on this, the two OH are the same. So whichever of them you choose to protonate, there is no problem. So protonation simply means addition of hydrogen. So I'll come here. That is basically the work of the acid, right, to protonate. So I'll come here, I'll say CH3, CCH3, OH, CH3, OH. Now, I want to flip this OH upwards and bring the CH3 down. It's still the same thing. So I'll come here, I put OH up, I put CH3 down. I put OH up, I put CH3 down. Now this is it. Now H2SO4, when I split it, it's going to be H plus, HSO4 minus. Now one of these O has a lone pair on the oxygen, which is going to pick up the H. On no account should you draw this arrow from a positive to a negative. No, it's always from the negative to the positive, or where you have electrons to where there is positive. All right, so once this happens here, this is what we're going to have. Okay, we're going to have CH3, C, OH, CH3, C. When that happens, here now becomes H2. This becomes water. So I'll put plus here. Remember, water is H2O. So this is now water. So step 1 is done. Step 2 says cleavage of the bond linking the protonated OH group to give water and form a carbocation. So this is what I'm going to do. All right, this is step 1. Step 2, I'm going to rewrite this. I might choose to continue. Okay, so I could just say this is step 2. Let's call this guy Step 2. Let's continue like that. Now, breaking of this bond, I'll come here. I'll cleave this bond like this, meaning that I'm breaking this bond and taking the electrons, putting it on this positive. Water will now come out as neutral, and this guy becomes a carbocation. So this is what we're going to have. We're going to have CH3, COH, which is this, CH3, C. If I break out this becomes plus CH3 and CH3 plus the water, which is this guy. If we break out this, the step 2 is you breaking this bond, cleavage of the bond linking the protonated OH. This was the OH I protonated to become this. So this is the bond I'm going to break so that I'll form a positive charge here plus water. So step 2 is done. Step 3 says migration of an alkyl or an aryl or hydrogen depending on what is actually present. So the migration is going to be from the adjacent carbon here. All right, so let's clean this stuff. So step 3 says migration. So I'm going to write this compound. This becomes CH3, COH, CH3, migration. Now this is the carbon bearing the positive charge. The adjacent carbon is this guy. So the two alkyl group is this and this. So I'm going to migrate any one of these guys. I'll migrate any one of this. So when I do that, if I move this point to this, just watch, to form a new carbocation. This becomes CH3, C. Now this CH3 is no longer here, right? The positive charge will now come here, and this CH3 goes on top. So the positive charge comes here. We have this CH3 that was initially here. When you migrate it, you're moving it with the bond, and you're taking it here. So we now have the new CH3 here, another one here, and another one here. Step 3 is done. Step 4 says loss of hydrogen from the other OH to form a double bonded oxygen. All right, so let's look at this. Now this OH now is this other guy, so I can choose to put the H this way. They say loss of hydrogen, right, to form a double bond. So the hydrogen is going out, not with the electrons. So this is what is going to happen. Now step 4, this is our step 4. Please watch, the step 4 is taking place here, right? This bond that is holding the H to this O will be broken. And once that happens, this bond comes down here. The hydrogen goes off. So this becomes CH3, C. You now form a new double bond. C, CH3, CH3 plus CH3. And this is the new compound, which was what I gave us initially. This H is coming out as H plus. Remember, from step 1, the acid was H2SO4 initially, but H was taken from this guy. So what we had left was HSO4 minus. And remember, a catalyst is not always
the H initially that was used to protonate the OH is now going to be used to form the H2SO.
Two factors determines the product that we obtain. Now the first one is the OH2 that will be protonated. Remember, the method is always protonation to form water as weight care. Sorry. If I have something like this, let's say we have CH3 plus I have something like this. Now imagine I have this. Hey, tell me. Look at these two compounds. This compound here. Which of these two OH? would actually be protonated. Remember, we said the OH group that is protonated and subsequently leaves to give a carbocation. So the stability of the carbocation form determines the OH group to leave. That means if I actually protonate this guy, subsequently, if this guy that will pull out, if this guy will pull out, this is a carbocation. Which type of carbocation is this? Secondary. Because this here is attached to just two carbon, this and this. Is it not so? Alright. Now, however, what if I had this? This was what I was protonated. This guy becomes plus. Which type of carbocation is this? So in this case now, which of them will be protonated? This guy, right? Because the carbocation that we form, of course, is actually more stable. Alright. Alright. Now this pH means phenyl, this phenyl. So I can write this guy, pH is actually the mu. So I can write this to show us now we have this. Now the big question is which of these two OH would be protonated? A or B? Please look up. Here, if you remove OH, please here, you to remember I would say the OH that will be protonated is actually going to be the one that will give rise to the carbocation, right? And if the carbocation is formed, the more stable the carbocation, the more easy the OH will be removed. Is it not so? Both of them, if you remove from here, this will be a tertiary carbocation, right? Because this is a carbon, this is a carbon. If you remove from here, this will also be tertiary. So both of them are tertiary carbocation. But then if you remove from here, there's what we call resonance, conjugated system. Remember, once the system has conjugated, once it's a conjugated system, it's bound to be a resonance. And the more resonance a compound have, the more stable. So if you actually remove this guy here, if you remember when I was using us here 261 or 260, I said conjugated system can be in such a way that a double bond separated from a carbon that has a positive charge from a single is not so. This guy has the single bond there, a positive charge, and the what? The double bond. So this guy will actually be more stable than this because of conjugated system. Right? Now this conjugated system, that means this guy can come here. I can put this plus here, and I can put this guy here. Resonance. So now, I want us to understand this. That I'm going to give us this example. We're going to solve with this example so that I can explain this. So in the case whereby you have stuff like this, which of these OH will be protonated? It is the OH that has the phenyl. Why? Because if this OH is protonated, subsequently, this is the one that will be pulling out. Is it not so? If this guy will pull out, there will be a positive charge. Once there's a positive charge here, this guy automatically look up. If I have plus here, this is still stationary. Carbon here, and carbon is not so. But this stationary is more than this other stationary because of regular. You understand? So therefore, imagine they give you something like this, and you consider to come and protonate this guy, you fail the question already. Right? You fail this. It's nothing like let's help you come back. Alright, so that is that for now for the second guy, we say migratory attitude. He said migratory attitude. Let me show something. The second guy is alright. Please look on. Now, H can migrate. Alkyl, commonly methyl can migrate. Aryl. When we talk about aryl, we are referring to substrate that possess benzene ring. Right? This is what we mean. So, three of them can migrate via 1, 2 shift. Now, imagine I have something like this. I have pH I love this breeze. Imagine how something like this. In this case now, the OH to protonate is not a problem because both of them are equivalent. Have you seen that? Yeah. pH, this is phenyl. Both of these carbon is actually having same cycle combination also. Yes. So the protonation is not a problem. But after protonating, the problem will now be what? Migration. So let's assume I protonate this guy and then becomes close. Something. I break it out. It becomes close. It's now time to migrate. I'm going to either migrate this or what? This. This is now where the aptitude comes in. These two guys, they have the possibility to migrate, you know, also. But the one that have more tendency will actually go first. So between phenyl and alkyl, which of them has a higher migration aptitude? Phenyl is under RU. And I told us RU has more what? Tendencies. Why? Because they are rich in what? Electron. Right? So this guy, now, in this case, it is this guy that will migrate. Right? So by the time you actually see questions like this, oh, you've already used it. The mistake most of us to make is that you just see a question like this, you start solving. You don't just start solving. What do you do first? You solve it first with your what? With your eyes. So that when you get to this point, if you want to migrate, if you have checked it out already, you can rewrite this image here and put your words here. You know it's the same thing. So therefore, pH is going to migrate because this guy has a greater attitude to migrate compared to what? To this guy. Alright. So if you now come and migrate this one instead of this, you tell the question again. Not two ways about it. So the first one is to know which of the OH to protonate. The second one is to know which of these to migrate. In the case where you have this will migrate higher than this. But what if this place were to be hydrogen? What will migrate here? Yes. He to have these two questions here for us to solve.